Okay, folks, in this problem, we're going to calculate what's essentially the enthalpy of combustion of arachidonic acid, which, as noted here, is this combustion of this acid is what helps to keep animals warm during hibernation. So first thing we need to do, of course, is balance the reaction. So I've already written it out here, but basically, here's our arachidonic acid. It's obviously a pretty big molecule. If you want, you can look it up on the web to look at its structure. But if you recall, combustion is simply a reaction with O2. And if we only have carbon, hydrogen, and oxygen in our compound, then the products are going to be carbon dioxide for complete combustion and H2O liquid. So all we need to do is balance it, and this stoichiometry indicated here is the correct balanced reaction. You should check this just to make sure that you are confident that you can balance it. So it's basically, again, arachidonic acid reacting with O2 is a combustion reaction to generate carbon dioxide and liquid water. So we're given in this table the enthalpies of formation of the compounds present in this, and remember to calculate enthalpy changes when we have enthalpies of formation. We're just going to take the products minus the reactants, and of course we have to multiply them by the appropriate stoichiometric coefficients. And so here we go. What we're going to do is our products are carbon dioxide, so we want the enthalpy of formation of CO2, and because the stoichiometric coefficient is 20, we're going to multiply that by 20. And then the other product is H2O liquid, which again, here, it's important that you look at the liquid. It's negative, it's going to be negative 285.8, but I'm just going to write this here, right? So those are our products, and we're going to multiply that by the stoichiometric coefficient, which is 16, all right? And then we're going to subtract our reactants, and our reactants are, of course, the arachidonic acid, all right, and which has a stoichiometric coefficient of 1, and O2, which would be multiplied by 27. But you recall that when we are looking at enthalpies of formation of elements in their most stable form, O2, oxygen, is the most stable form of oxygen, so that is equal to 0. So we don't need to worry about that one. So we've just got then the enthalpies of formation of CO2, and we'll just go ahead and multiply this out. From our table, we'll see that CO2 is negative 393.5 kilojoules per mole. And our H2O liquid multiplied by 16 is 285.8 kilojoules per mole. And then subtracting our arachidonic acid, which is negative 636. And again, this is where you do have to be careful with signs. But we're subtracting negative 236 kilojoules per mole. And so really, this simple arithmetic here, we just plug all the numbers in, and we get a value of, I'm going to go ahead and write the entire thing out, but then I'll talk about sig figs. So it's 11,806.8 kilojoules per mole. All right, so there we have the situation where we calculated delta H for arachidonic acid per mole by just simply using the enthalpies of formation. So let me know if you have any questions.